Limits from a numerical and graphical viewpoint. We write the limit as x approaches a of f of x is equal to L if we can make the values of f of x arbitrarily close to L by making values of x sufficiently close to a but not equal to a. If f of x fails to approach a single fixed number as x approaches a, then we say that f of x has no limit as x approaches a, or that the limit as x approaches a of f of x does not exist. Here we're going to guess the value, the limit as x approaches 1 of x minus 1 over x squared minus 1. If we look at numbers that are less than 1, we're looking at, say, x equals a half, x equals 0.9, x equals 0.99. We're trying to get numbers that are getting closer and closer to 1. And as we increase those numbers closer and closer to 1, we see that our function value goes from 2/3 to 0.53 to 0.50, and it stays around 0.5 as x gets closer and closer to 1. So we might guess that for values of x that are less than 1, the limit as x approaches 1 of x minus 1 over x squared minus 1 equals a half. However, we also have to look at the other side when x is a little bit bigger than 1. So we'll take values of x that are a little bit bigger than 1, say 1.5, 1.1, 1.01, etc. When x is 1.5, we get 0.4. When x is 1.1, we get 0.476. When x is 0.01, we get 0.497, and so on. And these numbers appear to be getting closer and closer to a half. So both using x values that are larger than 1 and smaller than 1, the limit as x goes to 1 of x minus 1 over x squared minus 1 looks like it's going to a half. In fact, if we look at the graph, the blue line, the y values on the blue line appear to be getting very, very close to a half as the x values get very, very close to 1. Notice as well that the x value at 1 doesn't exist. So in a limit problem, we don't need there to be an actual value at the limiting value. We need the function to be approaching a value when x goes toward the limiting value. Here's another one. We want to evaluate the limit as x approaches 0 of e to the 2x minus 1 over x. So a table of values is going to give us, for values that are a little bit negative, so a little bit close to 0, but a little bit less than 0. So for example, x equals negative 0.1, we get a function value of about 1.8. When x is negative 0.01, we get something about 1.98, negative 0.001, 1.998, so on. And it looks like it's getting closer and closer, probably to 2. If we look at values of x that are a little bit bigger than 0, we're going to see that when x is 0.1, we get about 2.2. When x is 0.01, we get 2.02. And again, these values look like they're going toward 2. So in this case, it appears that the limit as x approaches 0 of e to the 2x minus 1 over x is equal to 2. Here's another example. We want to determine the limit as x approaches 0 of 1 over x squared. So again, we're going to take a table of values. We're going to take some values that are close to 0 but a little bit bigger, and some that are close to 0 but a little bit negative. So as we approach 0 from the left, we get for negative 0.1, 100, and then 10,000, then a million, then 100 million. When we approach from the right, we again start at 100, then get 10,000, then a million, and then 100 million. It looks like it's getting quite big as x goes to 0. And so in this instant, we would say that the limit diverges to infinity. Here's another one. The limit as x approaches 0 of absolute value x over x. We take a table of values, and as we approach absolute value x over x for values of x that are a little bit smaller than 0, all the values look like they're at -1. And for values of f of x that are a little bit bigger than 0, for values of x that are a little bit bigger than 0, our values of f of x look like they're all 1. And so we would write the limit as x approaches 0 from the left of f of x is equal to -1, and the limit as x approaches 0 from the right of f of x is equal to +1. And so what this means is that since the two limits disagree, the limit as x approaches 0 of f of x doesn't exist. These are called one-sided limits. In order for a limit to exist, both one-sided limits have to be equal. Here's another example. We want to determine the limit as x approaches 2 of 1 over x minus 2. Again, we can look at a table of values. As we approach from the left, we've got y values of -10, -100, -1,000, -10,000. And again, those are for values of x that are a little bit smaller than 2. When we look at values of x that are a little bit bigger than 2, we get values like 10, 100, 1,000, 10,000. So it looks like the values are getting bigger, though the values that are less than 2 look like they're going down to -infinity, and the values that are a little bit bigger than 2 look like they're going up to +infinity. But again, we note that f of x is not approaching a single real number when x goes to 2, so that the limit as x approaches 2 of 1 over x minus 2 won't exist. That is, the limit as x approaches 2 from the left of 1 over x minus 2 is equal to -infinity. The limit as x approaches 2 from the right of 1 over x minus 2 is equal to +infinity. And the limit as x approaches 2 of 1 over x minus 2 does not exist. Here we'll talk about limits as x approaches infinity. We're going to let f be a function defined on some interval that starts at a and goes out to infinity. Then the limit as x approaches a of f of x equals L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. So if we want to estimate the limit as x approaches infinity of 2x squared minus 4x over x squared minus 1, we can go ahead and make a table of values again. So as x approaches +infinity, we might start from x equals 10, and then go to 100, then 1,000, then 10,000, and so on. And as the x values get larger, it looks like the y values go from about 1.6 to 1.9 to 1.99, ultimately to 2. And so we would say the limit as x approaches infinity of 2x squared minus 4x over x squared minus 1 is equal to 2. Similarly, if we want to evaluate the limit as x goes to -infinity of 2x squared minus 4x over x squared minus 1, we would again, by table of values, start looking at x values that are getting smaller and smaller. So -10, -100, -1,000, so on. Again, we notice the y values getting closer and closer to 2. And so the limit as x goes to -infinity of 2x squared minus 4x over x squared minus 1 is going to be 2. Let's take a look at some limits based on a graph. The first one I want to look at is the limit as x goes to -2 of f of x. So if you find where x is equal to -2, and you go up to the graph, the value that the graph is approaching very close to that is the value that we want. So as x approaches -2, we can see both the left limit approaches +2 and the right limit approaches +2. And so the limit as x approaches -2 of f of x is going to be +2. Let's look at the limit as x approaches 0 of f of x. Again, taking a look at the graph, as x goes to 0 from the left, we can see that we're tending toward -1, although we never actually get there. From the right, as we approach 0, we get a y value of 3. And so what we see is that the left limit is going to be -1, and the right limit as x goes to 0 is going to be 3. And so the limit does not exist. Next, let's look at the limit as x approaches 1 of f of x. From the left, we come down, and looks like we have a y value of about 1 as we come down here. As we come down from the right, it looks like we're heading toward y equals 1. Now again, we have a point at 1, but we're not looking at x equals 1. We're looking at what happens close to 1. And close to 1, we're pretty close to the y value of 1. So you can see here, as the x values get closer and closer to x equals 1, our y value gets closer and closer to 1, and same on the right. Finally, as x goes to +infinity, as x gets larger and larger and larger, the y values get larger and larger and larger. And so we would say that the limit as x goes to infinity of f of x is equal to infinity.